That's the idea. F of x is the same as y. So I'll let it equal 0. What do you want to take out of this guy? These guys?
X squared.
Okay. Make it x minus 4. What do you want to get in your next parentheses? Yeah, so what do you got to take out? What do you got to take out? Minus 9, yes. X minus 4. That good so far? Now how do I re-express this?
X minus 9 equals 0. X minus 4 equals 0.
Okay. Suggested next step?
Set both of them equal to 0. Set both of them equal to 0.
Not yet. I know what you're thinking. It's not perfect square, it's the...
Difference of squares.
There you go. Difference of squares. Very good. Anybody else observe that? Difference of squares here. Now what do?
Set them equal to 0.
Set them each equal to 0, and I have my 3 linear equations to solve. So there are the zeros of the function. In other words, this curve, and this x cubed thing is going to be a curve. It crosses the x-axis at -3, +3, and 4. Whatever it looks like, it crosses the x-axis at those 3 points. Those are your zeros of the function. You're also the solution to that equation. Yes, ma'am?
So is it just a coincidence, or is it safe to assume that you're going to have the same number of zeros as the highest power in your equation?
The highest, the degree of the equation, the highest exponent, that could be the number of zeros I have. Or it could be 2 less than that. We don't want to get into that. Let me show you. That's all right. I got time. I'll show you. This is an x cubed function. In this case, this guy's got, it's at -3, it's again at +3, again at +4. It goes something like that. Okay. And this is going to be characteristic of an x cubed function. It turns twice. I'm turning again, okay? And in doing that, it hits the x-axis 1, 2, 3 times. But it could look like this. I'm turning again, okay? So it still turned twice, and it only hit the x-axis once. So you're going to have either 3 or 1 0 for this guy. That's a good observation. All right, zeros is out of here. Let's turn over to page 444. Actually, the problems are on page 451. Solving systems of linear equations. That sounds kind of daunting, doesn't it? Kind of overwhelming. Systems of linear equations. But actually, all it means is, I got more than one linear equation, okay? That's what a system is. It's more than one. So if you have more than one linear equation considered together, you have a system. That's all we mean by a system. For instance, that's a system of linear equations right there. Just two equations considered together. Hey, I'm observing that these equations both have x's and y's in them. Tell me about the line that comes from an equation that has x's and y's in it. It's a slanted line, right? So I got me a couple of slanted lines, and unless they are parallel, which they could be, they're going to have an intersection. And what we're doing when we're solving a system of linear equations is we're finding the point they have in common. We're finding where they intersect. So that's basically what we're looking for when we're solving systems of linear equations. We're looking for their intersections. Now I want you to think just a second. If I have two lines on a plane, and you know what I mean by a plane, like on the screen, on the blackboard, if I have two lines in a plane, what can they do in relation to each other? They can either be parallel and never touch, okay, that's one.
They can intersect.
They can intersect at a point, that's another. They can be the same line and, in fact, overlap. Okay. So they can intersect at no points, parallel, one point, which is pretty typical, or every point, overlapping each other. Okay, that's what we're looking for when we're looking to solve a system of linear equations. Do they intersect at one point? If so, what's that point? Are they parallel? Okay, they don't intersect at all. Or do they overlap? Okay, they're the same line. Okay, so those are our three conclusions we're going to come to as we work these solving a system of linear equations. Hey, one thing you can always do is graph the things.
Dr. Rice.
Remember how you graph the things?
I love you.
What would you do if you were looking at this guy right here? Before you graphed it, what would you do? Yes,
Wouldn't you put that into y equals form?
that's a good idea. Solve it for one of the variables. Have y equals something or x equals something. Y'all familiar with that? So I could bring this guy over and this guy over here. And basically what I get is y equals 2x minus 2. Hey, what would you solve for on this guy? Probably x, since it's already sitting there all by itself, just a plain old x. So x equals
Couldn't you solve for y on both of them?
You could, but if you did, you get a fraction here, and typically we want to avoid that. That's typically what leads to some errors. All right, what are you going to pick values for here? X or Y? I don't know. Let's go ahead and pick one for Y. Let's say Y is 2. Okay. Add 1 to both sides. I get 3 equals 2x. Divide both sides by 2. X is 3 over 2. That's 1 That's a fraction or a decimal. That's a mess. If I pick values in the more complex side, if I pick these values to be whole numbers, I'm going to get whole numbers for the other. You like whole numbers? I like whole numbers. So if you want to end up with whole number things to graph, Pick whole numbers for the side that is the most complex. Pick whole numbers here, and you're going to get a whole number for what's left over. So in the first one, I'm going to choose values for x. It's in the most complex, unsimplified side. So what do you want to pick for x? What's good? 0. 2 times 0 is 0, minus 1, I get negative 1. What else you want to pick? 1. 2 times 1 is 1, up to a 2, minus 1 is 1. And I got 2 points. Supposedly, if I did it right, that's all I did. 0, negative 1, 1, 1. Got myself 2 points. And here's my first line, 2x minus y equals 1. Oops. Hey, what are you going to be picking, what values are you going to be picking on this second equation? Y's, right? They're in the unsimplified side, the all confused side. So make it easy on yourself. What do you want to pick for y? 0. 2 times 0 is 0. 8 minus 0 is 8. What else you want? 1. That's 2. That's 8 minus 2. That's 6. So 0, 8. 1. Uh-oh. We picked y's. Is that right? We picked y's for 0. We picked y was 0, so x is 8. We picked y is 1, so x is 6. Thank you very much. So 8, 0. And 6, 1. And I got me a couple of points. I have x plus 2y. Now here's one reason why graphing is not quite the most ideal way to find where they intersect. Do they actually intersect in a point where the lines cross?
No.
Not the way I drew it, they don't. But you know what? They actually do. With my thick pen here and less than accurate drawing, I missed the fact that they actually intersect at that point right there, which is 1, 2, 1, 2, 2, 2, 2. And I couldn't know if I really did miss the point or not unless I put 2 and 3 back in there for x and y and see, oh, you know, it satisfies both of them. X is 2, y is 3, satisfies both those equations. Not the ideal way to find the intersection. Once again, if you're going to be picking points, you will want to pick values from the more sophisticated, complicated side. And when you do, you have just, whether you know it or not, named that variable. If I'm picking x's, this is called, anybody heard this? The independent variable. You heard that before? This is the independent variable. It's the one I choose. So I choose, you know what independent means? It means free from restraints. I could pick anything for x. I could pick anything. I'm going to have to graph it, so I better be careful. But I can literally pick anything for x. It's independent of any restrictions or bounds. But once I pick a value for x, the y is dependent on what I just chose. So that means the one I solved for is the dependent variable.